we're going to look at Lagrange multipliers. So assuming we have this surface, the function z equals f of xy, and we would like to find the maximum and minimum values, that's the extreme values, and the point where they occur. But in addition to that, we would like to find this with respect to some constraint. And our constraint is a function, a curve, on the xy plane, call it g of xy is equal to k. So the method of Lagrange multiplier leverage on the fact that each surface provides us a chance to look at its level curves. So assuming the surface we have there, this generic surface I have, its level curves are, let me use blue. These are the level curves at different points, okay? Let's just make them circles. All right, so these level curves, you know what, let's make them green. I am very particular, so I'll make them green. Style, green. Okay, so these level curves are somewhere, so maybe here, there, and so forth. In addition to these level curves, we also have the curve on the xy plane, the constraint. All right, so the red constraint, so let it be this. Okay. So there is an intersection. It's always, the level curves are infinitely many. So it's always going to be tangent to one of them. So we know that the level curve, that each level curve is tangent to some tangent line, and that tangent line is orthogonal to the gradient. So over here we have the gradient of our function. For the green level curve here, but at the same time, the curve g of xy equals k is also orthogonal to the gradient, or its tangent line at this point is also orthogonal to its gradient. So we have the gradient g of xy. Okay, so what do we see? We see that these two vectors, these two gradient vectors, are parallel to each other. Okay, so that's the key in Lagrange multipliers. So since they are parallel to each other, there is a constant lambda such that, therefore there is a constant lambda such that the gradient of f is lambda times the gradient of g. Okay. So the method of Lagrange multiplier can be summarized as follows. Okay. So assuming we would like to find the maximum and minimum value, max and min values of a function f of xy subject to the constraint g of xy equals k. Okay, so the first thing we want to do is to find find all values of x, y, and lambda such that the gradient of f is equal to lambda times the gradient of y. So, and then we also have g of xy is equal to k. So this is going to give you a bunch of equations. So this is a system of equations. These two equations here is going to give you a system of equations. And then the next thing you're going to do is to evaluate f at all the points x, y that result from step A or part A above. And the largest from this value, the largest is the maximum value, and of course the smallest is the minimum value. Okay, so let's look at some examples. Let me look for a quick example. So the first example is we want to find the extreme values, that's the maximum and minimum values, extreme values of the function is f of x, y equals x squared plus 2y squared subject to x squared plus y squared is equal to 1. So this is our f of xy, and this right here is our g of xy equals k. So our k is 1 in this case. So the first step, let's find the gradients. The gradient of f is obvious, is 2x, first partial with respect to x, and then 4y, first partial with respect to y. And then we want the next gradient of g, 2x, and then 2y, okay? So, but before that, how about let's look at this surface, just a little bit of this surface before we proceed. If you look at this surface, this is obviously an elliptic paraboloid, and this is a circle, okay? So we're looking at an elliptic paraboloid, right? And on the xy plane, we're trying to see what are the maximum and minimum values of this elliptic paraboloid if we restrict it to this circle, x squared plus y squared equals 1 on the xy plane. So that's all we're trying to do in this problem. Okay, so we have the two gradients right here. The next thing we're going to do is we're going to look at what the parallel nature of the two gradients is going to give us. So remember that we're supposed to assume that the gradient of f is lambda times the gradient of y. So if that is the case, what do we have? Right? So we have that this will give us that 2x here. 2x is equal to lambda 2x, lambda 2x. Okay, so this part of the gradient of f and this part of the gradient of y. So 2x is equal to lambda times 2x. And then we now have that, I want to do everything in light blue. How about that? Let's style everything in light blue. Okay. And then we have we have 4y. This 4y right here is equal to lambda times this 2y. So it's equal to lambda times 2y. Okay. So we have that. And then we also have our function g of xy equals k. So we have x squared plus y squared is equal to 1. So we have three equations. Let's call this equation 1. Call this one equation 2. Call this equation 3. Okay. So we can see right away that equation 1 gives us, equation 1 implies that if you take the lambda 2x to the other side, you have 2x minus lambda 2x is equal to 0. And this is going to give you, if you factor out the 2x, you're left with 1 minus lambda is equal to 0. And this means that x is equal to 0 or lambda is equal to 1. Okay? Now, equation 2 will give us that 4y minus lambda times 2y, is equal to 0. So this implies if you take 2y out, you're left with 2 minus lambda, right? So this tells us that y is equal to 0 or lambda is equal to 2. Okay, so let's see which of these is useful. So let's start with the first set of values we got from equation 1. So now, if x is 0, what do we get? If x is 0, then equation 3 above, x squared plus y squared equals 1, would imply that since x is 0, we just have that y squared is 1, and this tells us that y is equal to plus or minus 1. So this gives us two critical points. So this gives us x being 0 and y being 1, and x being 0, y is negative 1. Okay, good. Now we can do another thing. We can also check if lambda is equal to 1. What do we get? If lambda is equal to 1, we can plug that into equation 2, right? Equation 2 gives us that let's see, equation 2 gives us that 2y, if lambda is equal to y, so I have 2 2y is equal to 0, this implies that y is 0, right? Y is 0. But now, if y is 0, equation 3 now implies that x squared is equal to 1, which tells us that we now have two critical points based on this value and this value. Actually, this is plus or minus 1. So this gives us x1, y0, and x negative 1, y0. Okay? Now, we can also say, okay, if y is 0, what do we get? But this already took care of that, right? When y is 0, that's what we're going to get. And when lambda is equal to 2, what happens, all we can do is plug it in here. And if we plug it in there, we get 2x minus 4x negative 2x is equal to 0, which means x is 0. So we already have x is 0. So it turns out these are the critical points. These are all the critical points we have, right? So let's look at our steps for the Lagrange multipliers. So the step says solve this system of equation, which we've solved. Then we're just going to plug it back into f. So if you plug in f of 0, 1, what is that? This should be 2. F of 0, negative 1, which is 2. Please check these answers. F of 1, 0 is 1, I think, and f of negative 1, 0 is also 1. All right, so that is that. Now, so this, our maximum values are 2, maximum values 2, and we get them at 0, 1, and 0, negative 1, and our minimum value is 1. We get it at 1, 0, and negative 1, 0. All right, let's modify this problem a little bit. Let's assume we still have the same problem or the same function, but now our constraint is the disk. On the disk, x squared plus y squared is less than or equal to 1. Okay? So we have this same graph, but instead of just focusing on the circle, we are looking at everything inside the circle. What is going on? Can we find a maximum and minimum value inside this disk, not just on the boundary of the disk? So it's still the same thing. We do the same thing. We get the Lagrange multiplier critical points. So we have these critical points, these ones, from Lagrange multiplier. All right. So this becomes an absolute extreme value problem. So we've got this critical point from the Lagrange multiplier method. Okay. Then you need a critical point where you need a local extreme value or values. And we know how to do that. All we need to do is to find the partial derivatives and set them equal to 0. Basically, they're regular critical points. All right, set this equal to 0, set this equal to 0. This means that we get x is 0 and y is 0, and the critical point here is 0, 0. So we have this critical point right here, okay? So we have 4 critical points from Lagrange multipliers, and then 1 critical point that is likely a local minimum, right? So let's see. If you evaluate, we've evaluated at these, the first 4 critical points from Lagrange multipliers. So we have that. All we have to do is we also just have to add this critical point, this 0, 0, and 0, 0 gives us 0, okay? So if we now look at this problem, our maximum value now, maximum value is 2, and minimum value is 0, okay? However, in this case, maximum value, in the previous problem, the maximum value was 2. And the minimum value, was 1. All right, and we can tell where we got the point where we got this from. Okay, I'm going to try another problem. Okay, so let's look at this problem. This is becoming too long, but it's fine. Let's see. 3. Let's find the points on the sphere. X squared plus y squared plus z squared is equal to 4 that are closest to and farthest from the point 3, 1, -1. Okay, so let's see, what does this problem look like? Let's see. So we have a sphere, all right? So this is what a sphere looks like. All right. Ooh, that's beautiful. So this sphere lives on the x, y, z space. So that, this is y, x, z. And then we have the point 3, 1, -1. 3, 1, -1, this point's right here, okay? We don't know if it's on the sphere. We're just going to assume it's not on the sphere, all right? So we want the point, actually, it shouldn't be on the sphere, right? We want the point on this sphere that is closest to this 3, 1, -1, and we want the point that's farthest from 3, 1, -1, okay? So in order to do this, we have to first of all get a formula for the distance of any point on the sphere from this point 3, 1, -1. So this distance should be d is equal to the square root, or first of all, how about we just assume that any point on the sphere, its coordinates are x, y, z. So let's just get any random point on the sphere. Let's call its coordinates x, y, z. All right. So this distance, the distance of this point, an arbitrary point, the distance of this arbitrary point from this green point is now going to be just x minus 3 squared plus y minus 1 squared plus z minus minus 1, which is plus 1 squared. So that's square root of all these things is d. Or we can actually make it easier. We can look at the distance squared. Why not? So our goal is to maximize this function and minimize it. We want to find its maximum value, which will give us the farthest point, and we want to find its minimum value, which will give us the closest points. Or rather, the maximum value is going to give us the farthest distance. The minimum value is going to give us the shortest distance from the sphere to the point 3, 1, negative 1. But finding the maximum and minimum of this function is the same thing as finding the maximum and minimum of its squared. So, and squaring the function makes it a little bit easier. We don't have to deal with the square root. Okay? So it turns out we have our f of x. Our f of xy is x minus 3 squared plus y minus 1 squared plus z plus 1 squared. Okay, and our constraint g of xy is x squared plus y squared plus z squared is equal to 4. Our constraint is just the sphere itself. So we're looking for the maximum value of this function, and we're restricting it to the sphere. So this is our objective function, and this is our constraint function. So now let's go with the Lagrange multiplier method. We want to find the gradients of f. Gradient of f. Actually, this is the function of 3 variables. Ooh, this is fun. So this is a function of 3 variables. So this is z here, and this is z here. All right. So we're going to be dealing with gradient with 3 components. So the first one is just going to be 2 times x minus 3. The second one is 2 times y minus 1. And the third one is 2z plus 1. This is fun. And then the gradient of g is 2x, 2y, and 2z. Okay. So if we go with, remember the key to Lagrange multiplier, the key is that this gradient, the gradient of f, is lambda times the gradient of g. So this is going to give us 3 equations already. All right? This is going to give us the equation that 2 times x minus 3 is equal to lambda times 2x. Let's put it that way. Lambda times 2x, and then 2 times y minus 1 is lambda times 2y, and that 2 times z plus 1 is lambda times 2z. And then, so let's call this equation 1, equation 2, and equation 3. All right, and then we have the constraint. The constraint is that, what is the constraint? The constraint is just the sphere. The sphere is x squared plus y squared plus z squared is equal to 4. So let's call this equation 4, right? Let's call it equation 4. All right, so we have 4 equations to solve. But you can solve this however you want, but there are things that are easy to see. From equation 1, we can see that 2x minus 6 is equal to 2 lambda x. If you solve for lambda, you end up, or you solve for x actually, you see that x is equal to 3 over 1 minus lambda. All right? Likewise, equation 2 is 2y minus 2 is equal to 2 lambda y. And if you solve for y, you get that y is 1 over 1 minus lambda. Okay? Right? 1 over 1 minus lambda. After some simplification. And the third one, 2z plus 2 is equal to 2 lambda z. If you solve for lambda, you see that z is equal to, solve for z actually, is equal to negative 1 over 1 minus lambda. Okay, so now what we can do is that we can plug this into our constraint equation, which is equation 4. So if we plug this into equation 4, what are we plugging? Plugging this for x, this for y, and this for z, right? So instead of x, we have 3 over 1 minus lambda. So instead of x squared here, we have 3 over 1 minus lambda squared plus 1 over 1 minus lambda squared plus 1 negative 1 over 1 minus lambda squared is equal to 4. So that's what equation 4 becomes, right? And I'll let you to solve to simplify this, but after simplification, just looking at it, after simplification, it's quite easy to see that you get 11 over 1 minus lambda squared is equal to 4. And if we rearrange things, keep rearranging, you will get 1 minus lambda squared is equal to 11 over 4. And this tells you that lambda is equal to 1 plus or minus square root of 11 over 2. Okay, this looks a little bit involved. Can I deal with this now? I think so. All right. Why? Because this is a value of x, it's a value of y, this is a value of z. All right. So we have two points. We have x. If you plug in these values for x, y, and z, you will get two types of values. For x, or two different values. If you plug in 1 plus square root of 11 over 2, when I did it, I got 6 over root 11. Where am I plugging it in? I'm plugging it into each of these for x, y, and z. Each of them has lambda, and we're taking the values of lambda here. There are 2 values of lambda here. So plugging them into these. So when I plug 1 plus square root of 11 over 2, I got 6 over root 11, 2 over root 11, and negative 2 over root 11. And when I plugged in 1 minus root 11 over 2, I got negative 6 over root 11, negative 2 over root 11, and then 2 over root 11. All right, to finish this problem, all you have to do is, all right, so let's call this, what do we call this? Let's give it a name. let's call this capital X1, and let's call this capital X2. All you have to do is to plug these functions or these values into f. In other words, this is f of 6 over root 11, 2 over root 11, and negative 2 over root 11. All right, and then plug the other one in there. Plug negative 6 over root 11, negative 2 over root 11, and 2 over root 11 into the function f. And remember what our function f is. That is this function right here, this function. Okay, so what do you get? I want to know what you get. What did you get here? What did you get here? Whatever you get, if you get the values you get, one of them will be the farthest distance and one of them will be the shortest distance. So, or the farthest and the closest. So I think this would give you the closest, I think. And this should give you the farthest. All right. I'm going to stop the video here because it's getting too long. I think you can finish the problem yourself.